Alright, so for the second problem that I'm going to present for part B is problem 4, and that is a differential equation, y double prime minus y prime is equal to cosine of 2t plus cosine of 2t minus 12 times a unit step function starting at 6. And then we are given these initial conditions here at the bottom to use along the way as well. So we'll get started. I just have that equation written again up here. And then we'll start by taking the Laplace transform of the entire thing. So we have Laplace of y double prime minus Laplace of y prime is equal to L of cosine of 2t plus the Laplace transform of cosine 2t minus 12 times the unit step starting at 6. So we'll break down the left side first. Laplace transform of y double prime based upon our equations becomes s squared times L of y minus s times y of 0, which in our case y of 0 was negative 4, and then minus y prime of 0, which in our case was 0. And then L of y prime becomes s times L of y minus y of 0, which is negative 4 again. So that's the left side broken down, and then we'll break down the right side down here at the bottom. So this thing in purple, L cosine of 2t becomes, just based upon our Laplace transform table, becomes s over s squared plus 4. And then the light blue over here is a little more complicated because it's a unit step function. We have to make it e to the negative 6s and then times the Laplace of whatever the function here that was multiplied by the unit step function, whatever that function was, but with a t plus 6 plugged in wherever we see a t. So that becomes the Laplace transform of cosine of 2 times t plus 6 minus 12. And we can see here that when we distribute this 2 in, it will be 2t plus 12 minus 12. So this will just end up being the Laplace transform of cosine of 2t. So we'll move to the next page then, where the left side of that equation from the previous page is written here, simplified a little bit. And then the right side just becomes, we transformed, Laplace transform cosine 2t became this. And then, as I said before, this part down here was just going to become the Laplace transform of cosine of 2t. So that just becomes another s over s squared plus 4. So we have two of these very similar terms, but the one just has e to the negative 6s in there. So next goal will be to isolate the L of y over on this side. And so we will pull those two terms together and make it s squared minus s times L of y. And then we'll also subtract the 4s and the 4 over to the other side. So that will look like this then. And the next step then will be to divide s squared minus s by everything over here to get L of y by itself. And then, so that looks like this, where we have s over s squared minus s times s squared plus 4 plus e to the negative 6s times the exact same thing as what was over here. These two are exactly the same. And then minus, oops, sorry, we'll try and move that out of the way. Minus 4s over s squared minus s, and then plus 4 over s squared minus s. So that's what we have at this point. And then there's going to need to be a little bit of partial fraction decomposition done here. Well, first what we can do is we can actually pull out an s term from the s squared minus s here. So it becomes s times s minus 1. And then for these first three terms, that will actually cancel out. And the s will actually completely go away in that situation for those three terms there. And then from there, we'll be ready to do some partial fraction decomposition. So we'll have three terms that we need to use a calculator to partial fraction decompose. The two terms in red are exactly the same, so they will come out to the exact same thing when they decompose, but the term in green will be a little different. So we'll do the two terms in red first. they will come out to 1/5 times 1 over s minus 1 minus s over s squared plus 4 minus 1 over s squared plus 4. And then over here, multiplied by the e to the negative 6s will be exactly the same thing, 1/5 times all of those same terms again, multiplied by e to the negative 6s. So I will not write those again just to save some space on the PowerPoint here, but just know that this here in parentheses is exactly the same as this term here in parentheses as well. And then we can't forget about these two terms, so I will show them on the next page here. So we have the minus 4 over s minus 1 that did not need to be decomposed, but then the other part of that decomposed into 4 over s minus 1 minus 4 over s. So we see that these two terms will end up canceling, the minus and the plus 4 over s minus 1. And so when we put that all together then, it looks like this, where we have 1/5 times these three terms plus e to the negative 6s times 1/5 times those same three terms. And then we have a minus 4 over s that came from the last two terms there. And so at this point then, we are just about ready to transform back into the original language. We have been in Laplace language this whole time, so we're soon ready to take the inverse Laplace. Yes, like I said, these two things are exactly the same. I just abbreviated them here just so we didn't have to write them all again. So this is that same function from the previous slide, and now we are ready to take the inverse Laplace and go back to the original language and find an equation for y. So when we do this, this 1/5 just carries along. 1 over s minus 1 from our tables translates to e to the t, and then s over s squared plus 4 translates to minus cosine of 2t. And then 1 over s squared plus 4 translates to minus 1/2 sine of 2t. The 1/2 comes in there because this would really be s squared plus 2 squared, meaning our a is 2, and we should have a 2 on top there. So when we transfer back, we just need to make sure, put a 2 in the denominator and make it 1/2. And then for the second part of this, the e to the negative 6s tells us unit step function starting at 6. The 1/5 just comes along. And then we're going to have the exact same equations here as we did over here, because this term and this term were exactly the same. But we will now need to be plugging into t minus 6 wherever we see a t in these terms. So we have e to the t minus 6 minus cosine of 2 times t minus 6, and then minus 1/2 sine of 2 times t minus 6. And all of those together are multiplied by the unit step function starting at 6. And then this term here at the end, minus 4 over s, just gets converted or inverse Laplace back into minus 4. So that is the final answer to the original differential equation. This function for y would solve that original differential equation. I also am realizing now that I think I forgot a parentheses here. So this is not all in the argument of cosine. The argument of cosine should end here. But yeah, that's problem 4.